So I'm really glad to be giving this talk after Aaron's talk because he gave such a perfect introduction. So I think like Aaron and like Partha, what I'll be talking about is approaches to speech recognition that are very different from the standard HMM-based approach, but they're sort of complementary. So Aaron and Partha worked on the acoustic modeling side of speech recognition. So basically the mapping between the continuous space of acoustic waveforms to the discrete space of phonetic units. And what I'm talking about here is the mapping between some type of subword unit, not necessarily phonetic, and words. Can everybody hear me, by the way? A little bit louder? I'll try. Oh no, this isn't going to do it. This is just for the video. My understanding was that battery died. I'll just try to be louder. Okay, so the gist of what I'll be talking about is, so like Aaron was describing, most modern automatic speech recognition systems depend on labeling words as sequences of phones. And as we move from more formal speech to less formal speech or conversational speech, that representation becomes increasingly more problematic because we start to pronounce words increasingly differently from the way that you would expect given their dictionary pronunciation. So the question is, can we obtain a better model of what's going on in pronunciation variation using some knowledge of human speech articulation? Okay. And this is really a pretty old question that people have been looking at in various ways over the years. And hopefully with new machine learning tools, we can provide new answers to this question. And the other note I wanted to make is that there are actually a lot of reasons that people study articulatory models. I'm personally interested in it from the perspective of pronunciation variation, but there are also motivations from noise robustness, language independence, which I won't really be touching on. Okay, so for the rest of the talk, I'll start by giving an outline of pronunciation variation and show some examples of where it occurs. And then tell you about two kinds of models based on graphical models. One which is a generative articulatory model, which will apply to classifying words. And the second, which is a discriminative model, which we'll use for transcribing articulatory features in speech data. Okay, so let's start with pronunciation variation. Before I do that, I want to show you a representation of kind of the standard HMM-based speech recognition in terms of a dynamic Bayesian network. Because that'll set the stage for the other dynamic Bayesian networks that I'll be showing. Okay, so here's a Bayesian network that encapsulates the type of model that Aaron was describing before. So this is a Bayesian network, meaning that each of the nodes in the graph corresponds to a variable, and each variable is associated with its conditional distribution given its parents in the graph, meaning the other nodes that have edges pointing to it. And the joint distribution over all of the variables is the product of the local distributions of each variable given its parents. Okay? So the main variables that we keep track of in a speech recognizer is the current word at every time frame t, the state index, like the HMM state index. So if a word has 30 states, then this variable runs from 0 to 29. The phonetic state that corresponds to that, given what we know about the current word and where we are in the current word. And that can be either deterministically given by a dictionary, or it might be non-deterministic if we assume multiple pronunciations. And then the acoustic observations, whose distribution is typically modeled as a Gaussian mixture for every phonetic state. Okay? Okay, so why is pronunciation variation a problem? So let me just give you a few examples of what pronunciation variation looks like in conversational speech. What I'm showing here is 4 words, probably sense, everybody, and don't. They're dictionary pronunciations in red, like you might find in any standard pronouncing dictionary, and then all of their actual pronunciations as transcribed by a phonetician in a particular conversational speech database. And next to each pronunciation is, I'm not going to kind of talk about what each of the phonetic symbols mean, but hopefully it's similar enough to what you've seen in dictionaries that you can pretty much tell what's going on here. Each pronunciation also shows the number of times that it was produced in this database. And let me see if I can get some of these to play so you can hear them. This is the word probably. Oh, I can't even get myself to hear it. That's why. Let's see.
Probably.
Can you guys hear that? Oh, you got a microphone. Okay. Okay. Oh, no, now I need to coordinate my hands. I don't know if I can do that. Okay. So let's see.
Probably.
Okay. Here's another probably. Here's the word sense, which might be a little bit hard to hear, but it should sound like it has a little T sound inserted in between the N and the S. Sorry, technical difficulties.
Sense.
And then here's the word everybody.
Everybody.
Okay. Can you actually hear me without the mic when I'm just talking? So? All right, fine. So hopefully you can see that these are extremely degraded pronunciations. The other things that should be clear here are, first, that the dictionary pronunciation almost never occurs. In this case, it occurs in 4 instances out of 89 of the word don't, and nowhere else in this figure. And also that each distinct pronunciation is extremely rare. So you can start to imagine what would happen if you tried to build a statistical model. You would run into sparse data problems. And here is a summary of all of the data in this database. So this is the number of pronunciations, number of distinct pronunciations per word as a function of the number of occurrences of the word in the database. So typically words that occur around at least 50 times will have on the order of 35 distinct pronunciations, and it goes up from there. So it's really a very big problem. Okay. So the way that traditionally this has been approached is with phone-based pronunciation modeling, where the idea is that now we expand the lexicon with different pronunciations for each word, and we predict those pronunciations using phonetic substitution, deletion, and insertion rules. So for example, for the example of the word sense that I showed, the dictionary might have this pronunciation, and then we might have an insertion rule for the sound T that would produce this pronunciation. And these transformation rules are typically of the form, some underlying phoneme becomes some surface phone in some left context and some right context with some probability. Okay, so you can have different rules that fire with different probabilities. So for example, in this case, we'll have the no phone becomes T in the left context N and right context S with some probability. Another very common rule is flapping. That, for example, is why we say butter and not butter. So a T becomes a flap in the context of a left stressed vowel and a right unstressed vowel, typically with high probability. And these rules can come either from linguistic knowledge or they can be learned from data, given enough phonetically transcribed data. Okay, and I should say that this kind of effect, this T insertion, is extremely common. And something like this happens in many different settings. Like, for example, in the word warmth, it's very often pronounced warmth. And this occurs typically when there's a nasal sound like N or M, followed by a sound that's produced with the lips or the tongue. And if the lips or the tongue are too slow to produce, to move, to produce the gesture that they intend, you can get this kind of intermediate state that sounds like some other phone. Okay. Phone-based pronunciation models fit into the dynamic Bayesian networks that I showed before, basically by adding another variable. So whereas before we just had the word, the state index, the phone, and the observation, now we have the target phone, which is what was expected based on the dictionary, and then the actual phone, which depends on the target, as well as possibly many other context variables that I'm not showing here, but that affect the distribution of the actually produced phone. So the target is exactly the phone that we had before, and the typical way that people model the actual phone given the target phone in context is with decision trees. And here's what a decision tree might look like for the phoneme T. So the root of the tree is the marginal distribution of the sound. So given that the dictionary predicts that the sound should be T, it might be produced as T 40% of the time, as just a T closure without the turbulent burst sound at the end. 30% of the time as a flap, 20% of the time, or it might be completely deleted 10% of the time. And then if the previous phone is stressed and the following is unstressed, then that's the, oh wait, that's the wrong one, sorry. If the previous is stressed and the following is unstressed, then we're in that flapping regime where we're very, very likely to flap, and so on for other kinds of contexts. So the idea is you have a tree like this for every possible phoneme in the dictionary, and that predicts the distributions of the different actual phones in different contexts. Okay, so the problem with that kind of model is that, well, basically it doesn't tend to work very well. Like I suggested before, we often run into sparse data issues, and we also run into something a little bit more subtle, which is false homophony. So many words tend to sound alike in a phonetic representation, or tend to have the same phonetic transcription, because it's just too coarse-grained a representation. It doesn't account for much more gradual pronunciation changes that can occur. So another approach that some people, including myself, have been looking at are articulatory models, which alleviate these two issues. And they're inspired by ideas in articulatory phonology, originally proposed by Broman and Goldstein at Haskins, and also by autosegmental phonology, proposed by John Goldsmith here. Not when he was here, though. The idea is that instead of a single sequence of phones to represent a word, I have multiple sequences of, or multiple tiers of features. This is a different use of the term features than what people might be used to in machine learning, but this is a linguistic term for these multiple tiers of units. And the actual realizations now are straight from the dictionary, not through substitutions, insertions, and deletions, but through these multiple features going in and out of sync with each other, and through reduction, where an individual articulator might not reach the target location that it was going for. And to make it concrete, the particular articulatory feature set that I'll be using is based on the one in articulatory phonology. Without going into too much detail, it's based on the locations and constriction degrees of different articulators. So the lips, the tongue tip, and the tongue body. And then the glottis, or the vocal cord state. And the velum, or the soft palate, which toggles whether air from the lungs is going through the nose for a nasal sound or through the mouth for an oral sound. And when we quantize their values, in this case to those values that are discriminative for words in English, but of course you could do the same for a different language or language independently. And so each of the features has between 2 and 8 values, typically. Okay. And just to give a sense of how complicated this dance of the articulators are, and also I thought it would be appropriate to bring Ken Stevens yet again into another talk. I'm going to show a video of, this is an X-ray video of Ken Stevens talking. Just a sec. Hold on. And I'll play it for you at some point, but let me just start by pointing out what you're looking at. So this is a side view of Ken Stevens. These are the lips, the teeth. You can see the contour of the tongue here. This is the velum, which is going up and down for nasal versus non-nasal sounds. You can't really see what the vocal cords are doing. They're someplace down here. And let me actually play it for you.
The tet, the tot,
Can you hear?
the tech, the pen, ed, eda, eg, ega, ea. Why did Ken set the soggy net on top of his deck? I have put blood on her 2 clean yellow shoes. Stop.
Okay. Unfortunately, we're not allowed to do X-ray studies like that anymore. But yeah. Oof. That sounds about right, but I'm not really sure. Ken Stevens is in his 80s. He's okay. Anyway, so hopefully that gives a nice idea of just how complicated the motion of the articulators are, and kind of makes us sympathetic to the fact that they may not always reach the targets that we intend them to reach at the time that we intend. And so in an articulatory model, we have different interpretations of what causes these pronunciation variations. So instead of substitution, insertion, deletion rules, like I said, we have asynchrony or reduction. So for example, in that example of the word sense with an inserted phone, instead of a phone insertion, this is caused by an asynchrony between the soft palate and, in this case, the tongue, which is supposed to make the S gesture. Other examples are vowel nasalization, where instead of a nasal consonant like an N, that nasal consonant just appears as nasalization on the vowel before it. So in terms of phone-based model, this would be called a phone deletion. But of course, the nasal consonant is still alive as a feature modification of the previous sound. And this can also be described in terms of asynchrony between 2 articulators. So in examples like the word probably that we saw before, these would also be considered phone deletions, but they're caused by reductions in this case, lip opening and closing gestures. And there are also more exotic things that can occur. Things that appear to be actually exchanges of 2 phones can also be caused by just a little bit of asynchrony between articulators. And in general, a lot of substitutions are just a lot more gradual than an entire change of a phone. Okay, so what I'll show now is a dynamic Bayesian network that implements ideas from this model. And if you remember what the phone-based model looks like, this should look kind of like a bunch of phone-based models with relationships between them. So again, we're going to have, in each frame, we're going to keep track of the word. And now instead of a single state index variable, we have several state index variables, one for each feature. In this example, I'm showing 3 features, but in practice, we can have as many as we want. Then for each feature, we have a target position. And that can be given by a dictionary, just like the target phone was given before. Given the target position, we have a distribution over the actual feature value. In a context-independent model, that's just a confusion matrix. Given what the target was, we have a distribution of what the actual is. And then we also have a model for asynchrony between these tiers. In this case, we have one asynchrony, which are modeled as soft asynchrony constraints. So we have distributions over how out of sync the streams can get. In this case, we have a constraint on lips versus tongue and tongue versus voicing, but these can also be arbitrary. So this is a context-independent model, and then to make it a little bit more powerful, we can add more context, just like we did with the phone-based model. So each of these actual feature values can depend on many, many other variables other than the current target. Question? Yeah?
No, 5 more minutes.
Oh, okay. So I'll breeze through the second part. And like in the phone-based model, we can model these distributions, again, with context-dependent trees. So in terms of the tools that we're using, they actually look very similar, but we end up with a much more complex model that's sensitive to states of specific articulators. And I should say that while the model looks a lot more complex, it actually has a lot fewer parameters because by virtue of its being a factored model. So rather than having a separate probability for each phone, we only have probabilities for each feature, which has much lower cardinality than the phones. Okay, I'm going to skip this part and just go on to experiments. So in word classification experiments, what we're doing is we're given manual labels of the articulatory features, and for each word in the vocabulary, we compute the probability of that word given the features. And then what that gives us is a ranked list of the words in the vocabulary, and then we output the most likely word. This is kind of like an idealized speech recognition experiment. We're just recognizing one word at a time. And here's how our models do compared to phone-based models. The yellow ones are all various phone-based models, and the blue ones are feature-based models. We tried various different phone-based models, including the very fanciest one that we could find in the literature. And our context-independent feature-based models do almost as well as the very best phone-based models, while the context-dependent feature-based models outperform include all of those phone-based models. The performance improvement might not look too impressive. It's about 3%, but in terms of speech recognition, that's actually considered a very large improvement because it's typically very difficult to improve speech recognition accuracy. So the second experiment, which I'll kind of breeze through, is our attempt to generate more articulatory labeled data. So for the first experiment, we used very small sets of manually transcribed utterances. And now we'd like to do some automatic transcription so that we can increase the size of training data that we have. So our job here is, given that we have a known word transcription and the acoustics of a speech utterance, we'd like to find the values of the articulatory features at every time frame for all articulatory features. So we're given a waveform and the word, and we'd like to produce something that looks like this. And so we'd like to use this to generate articulatory labels for a much larger set. In this case, we've moved to a more discriminative model, a conditional random field-based model. These are undirected graphical models of a conditional distribution of the target variables, which are hidden given the observed variables, which are in our case the acoustics and the words. Most of the time when people use conditional random fields, this is the general form of the conditional distribution in a conditional random field. Most of the time people use log linear functions over subsets of the variables in the conditional random field. In our case, we have a combination of deterministic and non-deterministic factors. So the non-deterministic ones we do with log linear factors, just like everybody. The deterministic ones are separate. And this means that we have to do inference a little bit differently from how most people do it in CRFs. And I'll get back to that. I won't go through all of the details of the CRF, of course, but I wanted to show you what it looks like. It's actually a very similar structure to the DBN that I showed before. These little squares correspond to factors, individual factors in this product. And so we have one factor for classifiers of articulatory features. In our case, these are multi-layer perceptrons. One factor for transition probabilities, and one factor for asynchrony modeling. Okay. And this looks very complicated, but actually in terms of inference, it's much simpler than the DBN that I showed before, because all of the log linear feature functions can be collapsed and to make the model essentially look like a linear model, so very similar to an HMM that you can do inference with dynamic programming, where the deterministic constraints, like the dictionary, is just a constraint on the dynamic programming. Okay, so that basically serves to make the dynamic programming very efficient. Do I need to? So let me just wrap up. So we've gotten improved performance on articulatory feature transcription. The thing that's much more, these numbers that probably are not very meaningful to people here, the thing that's much more exciting to me is that you actually get very very interesting analyses that are possible when you can see these forced alignments and possibly ultimately actually learn something about speech. So I'll end there. To conclude, articulatory models allow us to have much more parsimonious as well as detailed representations of pronunciation variation. I've shown you two types of experiments, word classification and forced alignment, where they've been successful. And there's a whole bunch of ongoing work to improve the models further. And I'll stop there. Thanks.